All I can say, gentlemen, is welcome again, and I know it's a very, very warm night, so good to see a few here. It's going to be a really interesting night. I can see that Chris has brought in a few bits and pieces which are already starting to draw attention, and nice things made out of bits of metal. We all know that if we've got the best rig in the world, we're not going to get anywhere unless we've got a decent antenna to get it out on the air. So hopefully tonight Chris is going to be able to explain to us a little bit about antenna design and how to put some together that's going to be good for us to actually put together in our own shacks. So I'm not going to say any more other than to say a big thank you to Chris for coming in to do this, and hand over to G4DCH on his antenna design masterclass.
Thank you. I suppose I'll start by sort of a bit of background, which I have sort of told people about anyway. What right do I have to teach anybody how to do antenna design? Well, I've been at it 47 years, so I know a little bit. However, I started actually at British Aerospace in Bristol. And just to put everybody in the picture, my boss, who was quite high up in the Institute of Electrical Engineers, he was one of these people who would adjudicate papers that were put into things like electronic letters and the IED publications, etc. So he was a highfalutin guy. But his mantra was simple: give me a good radio amateur rather than somebody who's got a whole load of letters after their name because they've gone and done wonderful things at university. So that's, if you like, how it started, because I don't have a degree in electronic engineering. I went to university, admittedly, but I don't have a degree in electronic engineering or electronics or physics or anything to do with electrics. My degree is in chemistry. But in 1974, I was working as a lab technician at a school. And the lab tech, no, sorry, I was working at that time as a teacher at the school. And the lab technician was a great guy, had a G8 license. And he said to me, because he knew I was interested in radio, why don't you go and get your amateur radio license? So I boned up on all of the things that you have to do, trotted down to Western Tech College and took my exam, which in those days was a 3-hour exam, all written, sort of 10 pages long or more on various subjects, on blank sheets of paper. Yeah, completely different from anybody that's taken licenses for that. So I did that. And because I lived in Burnham-on-Sea, and out from my bedroom window, I could see a whole load of radio masts. Once I got my G8 licence, all I had to then do was shimmy across the fields, tap out a few things on this keyboard, and lo and behold, moved up from my G8 licence to a G4 licence. And it was not long after that that I decided to give up teaching, chemistry, science and all that sort of thing, and went for an interview at British Aerospace, antenna design group. And basically they said, do you know anything about antennas? And I said, yeah, I made one of these, and I made one of those, and I made one of that, and I did that, and I know how to tune this, and I know how to... Oh, okay. When can you start? And I thought, brilliant. So I dug the tunnel out of the school and ended up working as an antenna design engineer at British Aerospace. However, I was used, like everybody else in here, I knew how to make a 2-metre antenna, I knew how to make an 80-metre antenna or a 20-metre antenna and all of those sort of things. So the first job they gave me was at 8 gigs. in satellite communications. However, that has stood me in very good stead throughout my 45 years. Anyway, that is history. But I think one or two people were, especially Jeff, he came up to me, Chris, he said, you're not going to go on about microwaves and all that sort of thing when you're going about antenna design. I said, Jeff, do not worry. I've got a lot of practice behind me. I have designed antennas from 10 kilohertz, and that was a really big antenna, that long. All the way up to 50 gigahertz. I have made them out of coat hangers. I have made them out of plastic. How many people have made a plastic antenna? How many people even thought that you can't make an antenna out of plastic? You go up into the microwave region, yes you can. They do amazing things in plastic. Plastics. Big word, that. So I've made antennas of all different sorts, shapes, sizes. Even antennas, because I've worked for what is quietly known as the Sneaky Beaky Brigade. That's places up there in London where they don't have names on the door. Or if they do, it just says Mr. Smith. And I've made antennas that don't look like antennas, and I've made antennas that you can put into things and they don't look like antennas, and yet they still all have to work and do exactly what it is on the tin. Now, let's get down to some business. How do you design an antenna? Now, most of you, I suspect, have bought an antenna. You might have even made an antenna from a book. But not how many can actually say they designed an antenna. And if you had to design an antenna, where would you start? What would you need to know? What is it is about an antenna that actually says, okay, I've read that in a book, a G5RV, and I've made one, and I've put it up. But you're going on somebody else's word that this thing does what it does on the tin, even if you go and buy one. And that's a big problem. You go and buy one, and what it actually says on the tin is a bit like the Prime Minister of this country at the moment, and you can't necessarily believe what it says. Sorry. Anyway.
True.
So, what is it you think that you need to know at the beginning before you design an antenna?
The frequency.
Yes, you need to know the frequency.
Speed of light.
You need to know the speed of light. That's a good thing to know about. Anything else?
Where you want to put it.
Where you want to put it?
Do you want to use a feeder?
Do you want to use a feeder? Right, let's start designing an antenna and see whether or not you know the difference between one thing and another. Here comes the good bit. This is knowing your knowledge about antennas. Now, first of all, frequency. What's the thing associated with frequency? We're not really interested in frequency, we're interested in the other thing. Wavelength. Right. Now, got that? You understand that? Right. What's the difference between those two?
What's half wavelength, what's full wavelength?
No, that's just L. That's nothing. I didn't put a lambda in there, did I? I just called that L. That can be anything. That could be 80-metre antenna and 3 inches from that side to that side. Whereas an 80-metre antenna, that's got to be 40 metres across there. So what's the difference?
It's one's unknown, one's known, is that really?
The length.
This one
Resonant.
is resonant. Okay. So what does that mean if you've got a resonant antenna?
It's a fixed portion of the actual frequency that you're talking about.
Yes, so?
So it could be a half wave or a quarter wave or a 5/8 wave or a just wave or what.
What does that one mean if that antenna is made like that?
Specific frequency.
Yes,
Tuned.
Without a tune.
but if it's tuned, no, forget the tune, it's tuned because it's exactly lambda by 2. It's tuned.
Will it?
The thing that everybody needs to remember is it actually produces root mean squared of the input signal compared to that, which is 1.414. So actually, if you've got a resonant antenna, you've got more power going out of it than you have if you... And the reason why I say that is because if you put up a lambda pi 2 dipole, which is, if you like, perfectly resonant, but you put up an G5RV, which is not, you will find that that works better than your G5RV. So when people say, I don't understand why it doesn't seem to work right, because it's not resonant. Now, that brings us on to the next thing that somebody said, feeder. Now, this, go back to that one there for the moment. And this is what I say about learning about antenna design and what design means. Here we go, our lambda by 2 antenna. And somewhere down here, we've got that. And we've got to somehow connect that bit to that bit. And this is where a lot of people get completely the wrong thing. Because somewhere along here, you've got this meter. VSWR meter. And everybody knows what VSWR means, doesn't it? Do you really know? How many really know what VSWR means? Not, I know what the words mean, but what does it really mean?
Is it a ratio of the reflected power to the...
Yes, but of what?
The voltage.
Of what?
The signal.
No, that's the bit you all get wrong. It is of the system.
It is part of the system.
The system, and the system consists of whole loads of stuff. Bits of something in there, connecting this transmitter through that into whether or not it's ladder line, coax, whatever it is that you've got something in between, and then you've got that antenna.
Making up the system.
Making up the system. Now, you go back to this thing, and you connect that one up through to there and to that, right? That then, if you like, makes a different system. And you get that, and it all works out, and this thing says, ooh, what, 1.1, 1.2 to 1. But that's not what is there. And you don't even know that what you've got there is what you've got there. Because you've got all this crap in between. And that crap includes the cables, it includes the connectors, it includes where you've wound it round the house and up the chimney and everywhere else. And it's made this value down here. But it's not necessarily what that is. That is a different thing altogether, unless you connect you connect a meter directly to this point here. You don't know what you've got. Now, when you're in the professional world, now, some of you have got one of these. 30 quid's worth of absolutely pure gold. Right? When I started, one of these would cost you the best part of £20,000.
Wow.
Now you buy them for 30 quid. Not quite the same as what you get for £30,000, but not too bad. The last one of these I was working with, by the way, cost £200,000 because it went up to 50 gigahertz. But this tells you the story. But what you need to do is to connect this through all of that, first of all, and then, if you like, cut it off there. You've got to recreate that bit completely to get what that is. So, if you've got 50 foot of something, cable, ladder line, whatever it is, then you've got to put 50 foot of ladder line and cable onto this to null that all out, so that this is basically flatlining with all of that disappeared. Then you can connect it to find out what you've got here. So that is very important. But most of you don't do that. You do this, and of course a lot of you, if you like, add one of these other boxes which has got something along those lines in it. An antenna tuner unit. And what that is doing is getting rid of all of the crap that you created in and around here. All that is doing is making sure that your transmitter sees what it wants to see. Now, the interesting thing about most transmitters is what? Is the output.
50 ohms.
And it's got an output connector on it, hasn't it? And what is the output connector on your transceiver? No, I said what is the output? What is it? It's a connector. What sort of connector? An SO239. Which of course everybody knows is not a 50 ohm connector. Anybody in this room thinks that is a 50 ohm connector? No, it's not. It was made by the telecom people, and it is 75 ohms if you're lucky. It is not a 50 ohm connector. So when you're measuring all your stuff here, and you've got SO239s, PL239s, and all the way up there, the first thing you've got is all this mismatch going on because you haven't got the right connectors. Now, if you were professional and you had a professional piece of kit, of course you'd have something like an N-type, which is a 50 ohm connector, balanced, proper job. Or TNC, BNC, all of those. That's the 50 ohm version of the TNC, because I do know that there is a 75 ohm version as well, and it's a 75 version. So don't pulling me up on the thinking, oh, but I got a 75. Yeah, I know that.
So that then, Chris, that's the reason then why on professional signal generators and whatever, like the Marconi I've got, it's an N connector.
It will be an N-type connector. That's why on there you've got, if you like, SMAs.
Yeah.
These SMAs are true 50 ohm connectors.
Chris, what about if you're saying N connector? What if you put an N connector to a PL259? What would that do?
Cock it up. Look, basically speaking, if you're doing what you're doing, let's look at it this way. Here, you have a 50 ohm N-type connector. And then the next thing you're going to do is put a PL259 there, which at best is 75. So immediately you have a mismatch of 50 to 75 there. So you've already got a mismatch. Right? So that's a mismatch. Anyway, even if you used an N-type connector, you have a mismatch. In any one connector, you will have a mismatch equivalent to 0.2 of a dB per connector. So if you've got 5 or 6 connectors going down your track, your piece of coax, whatever it is, and you've got joins in it and everything, every time you've got a join in it, you've lost 50, your 50 ohms goes out the window. Now, unfortunately, what this hasn't got is a thing known as a TDR. I don't know how many people have come across TDRs. Oh, one or two. Yeah, I know Don would have come across. It stands for a time domain reflectometer. What it does, it sends a pulse signal down your piece of cable, and wherever it sees a joint or a mismatch, it will send it back, and you can see it as a blip on the screen. And if you've got a short circuit at the end, it suddenly goes dunk like that. And if you've got an open circuit at the end, it goes whoosh like that. And if you've got a connector that isn't sort of quite right, it sort of does weird things, but it tells you. And I mean, if you're in the professional world, if you're putting this into an aeroplane, a ship, a submarine, and you want to think, and it's going through 8 bulkheads, etc., etc., and you think, it's funny, it's not working and I don't understand. You use your time domain reflectometer, you send a signal down, and hopefully you think, there's a nasty anomaly on bulkhead number 3. So we go down to number 3 and then start taking things apart and seeing whether or not it's all going to happen. Right, so that's a few fundamentals about antennas without even getting into antenna design. Right.
So why do all the manufacturers fit that bill going on the back of the ring?
The answer to that is I really don't know. It started back a long, long time ago when they came across the fact that PL259s were cheap and cheerful and easy to make, and if you like, a radio amateur wasn't trained. Right, when I first started work, one of the things I was trained to do almost straight away was, one, be able to put an N-type connector on a coax cable, whether it was RG314, RG58, 213, 214, whatever, and then you'd be shown how to put precision SMAs on, TNCs, and so on and so forth. So you were trained properly, like somebody on the shop floor would, how to put connectors onto proper coax cables, because they could be very, very important. If you're putting stuff into an aeroplane, in inverted commas, you can't make mistakes, because aeroplanes have a habit of falling out of the sky when people make mistakes. Right, let's get on to trying to figure out designing an antenna. Simplest antenna, I call them monopoles, so I hope you understand what I mean by that. Basically a vertical single thing. There it is, an antenna. This is your ground plate, there's your monopole, and we're going to be very good to start off with. We're going to make that lambda by 4. So there we go, that's the easy bit. Now, what do we know about this point here? Basically, what we'll do, because it's on this ground plane, we'll consider it as being at Earth, wherever Earth is.
75 equals.
Right, what do we know about this point there?
In the air.
Right, okay, let's say,
in the air.
what is, if this is connected to the ground, that's 0 ohms, because it's connected to ground. What have you got up there?
Infinity.
Thousands.
Sorry?
Thousands of ohms.
No, you don't.
Infinity.
What do you have?
Thousands of ohms.
This theory,
Roughly 300.
Oh, okay.
That is the radiation resistance of the monopole, 300 ohms. This is great, great news. Why is it great news? Because if you've got 0 there and 300 there, what do you know about somewhere up there? You know a point somewhere up there is 50 ohms. So now, if you like, you can connect your piece of coax cable to this point. And you've got your nice 50 ohm point. Now, the trouble is if this is for 80 metres, this is now 20 metres long, and this thing could be about 15 to 20 feet up in the air. So what we can do, very cleverly, we can do that. We can put a bit of coils in, and now our 50 ohm point, if you like, comes out there. I'm not going to do all the coax cables, but we'll just assume there's our 50 ohm point. And this thing is now a little bit shorter. And the big advantage of this type of antenna is if this is now 0 ohms and we're putting something watts in there, and watts, as we know, we all know is that bit. Okay. What do we therefore know about this point here, if that's 0 ohms, about these two things? V has got to be 0 because it's basically grounded, and so I has got to be high. So if you were plotting a graph, right, of up here, the voltage and here against height, it will basically do that. And if you like, the current will do the reverse. So that's the V curve and that's the I curve. Now, as you can see, that's 0 and that's going up to big V, right? Now how many can do maths? Oh dear. Oh dear. Who can do maths? Right. Right. Now, here we go. Maths. W equals V times I. But we don't want I. We want to know V. Right? And that is I by Ohm's law. Is that right? V equals IR? Yeah. So we've got V squared over R. Right. Now if you try and put that, we know is 300. Let's call that 100. Multiply that together because that goes over there, and that equals V squared. So that's 30,000 volts. And if you take the square root of that, up there is a very big number. So don't go and grab hold of it. Danger. It will hurt. There's no current up there, so you don't have to worry because the current's all down this end. And current isn't really going to hurt you in this case because you've got no voltage. So there's a thing less to worry about. Okay. I won't dwell too much on maths, so don't worry. It's one of the things, by the way, how many people can work in dBs and watts? How many can convert watts to dBs, dBs back to watts? Actually, it's very simple. Right. So you know that 1 watt is 0 dBW. Right. You should also know that if you double dBs, so you've got 2 dBs, right, then V has got to change by 3. So 2 dBs is 3 watts. So if you work on these sort of things, 10 dBs actually is 10 watts. 20 dBs is 100 watts, and so on. But if you take 3 dBs off of 20, that's 17, but that's 50 watts because you've taken 3 off. So if you can actually do simple little sums, if you go and work it through yourselves at home in your spare time while you're trying to go to sleep, you can actually, it's not an absolute, but you can work a lot of these things out in your head. 10 watts, 10 dBs, right? You drop down 3 dBs to 7 dBs, Ws. Well, that's got to be 5 because that's got half. And so it goes on. And you can do all these jiggery-pokery things in your own head by adding and taking away 3s, and you know you've got to halve it and double it and so on and so forth. So it's not as difficult as what it may initially appear. And then you can also use a calculator, but you've got to know that you've got to do 10 log this and 20 log that, depending on what you're working on. Enough of that. Okay, so this is our antenna. Right. Now, and this is where the interesting bit starts. Here we go. Here's our antenna. And we'll fed that like that. That's good. Now we can do things to that antenna, can't we? Now, first of all, this is on the ground plane. What do we know about the ground plane? This is, well, yeah, it's sort of conductive. And what sort of antenna patterns do we get out of this? In one of the things that we did mention about the fact that, you know, when we design an antenna, what are the things we need to know? One of the things you need to know is actually what antenna pattern you want out of it.
Well, it's unidirectional.
That's omnidirectional.
It's omnidirectional in which plane? If you look down on it,
Horizontal.
it is horizontal. But if you are looking that way on, right, it will probably look something more like that. And this thing here, and that thing there, is caused by this ground plane. If it's infinite, then it just does that. If it's not infinite, you start to get these things coming in. And that's the big problem. So here we are. Oh, I did that wrong. There we go. A man sitting in a car. And he's got his 2 metre whip stuck up there. That is not, in any shape or form, an infinite ground plane. In fact, even at 2 metres, it barely makes lambda by 4. So this pattern, if you like, if there's nothing to hold this pattern up, the answer is it's going to flop down. So the pattern that you get out of that does that. Now, one thing you have to remember, I should have brought it with me and I've forgotten, I'm terribly sorry. Right. How many people have heard of a thing called an isotropic radiator? Oh, 1 or 2 of them, isotropic radiator. Right. It is the standard unit for antenna gain measurement. It is a spot in space that is basically emitting RF in all directions. Basically, if I had a circular balloon, that's what it would look like. That's an isotropic radiator. Now, the thing is this. One of the things that you all have to remember, how many people, right, know, let's think, whose law is it? Is it Newton's first law? Right, yes, Newton's first law. Matter can be neither created nor destroyed. Right. You've got your balloon, that's all you've got. And it doesn't matter what you do, you can't get any more than what you've got in the balloon. So if you put it on a ground plane and you squash it flat, or try and squash it down there like that, because you've now got a ground plane on it, it's a very floppy balloon, so it splays out. And because it splays out, obviously in this plane you get gain. Now the other thing is that, as you all know, radio waves are made up of 2 components. The electrical component and the magnetic component. Now, the thing is that the electric component cannot propagate across a horizontal surface. So this bit don't go nowhere. And this bit, the electrical bit, actually can't transmit up a monopole. It can only transmit out from a monopole. So there's nothing going up there, and there's everything going out here. So you take your balloon and then you push it down the middle like that. And that's the bit going down there. And of course, as you push it down, more of this pushes out. Right? Which is, you get what we've got there. The problem now is, if you go and remove some of that ground plane, it just sort of over the edge, like this. So it's going over the edge. So when you read this thing, and this goes back to what we were saying about buying stuff and antennas, and you read what's on the tin, and it says this is 6 dBi. Whee! Against what? They measure everything against what's called a 20 lambda ground plane. Well, if this is 2 meters, 20 lambda, right? 20 times 40 meters in each direction is the size of the ground plane. Not your car, which is sort of at best a meter across. So this 6 dBs isn't going out there, which is where you think it's going. Most of it is sort of going down there, probably following you behind in the car. So, don't believe what you read on the tin of these sort of things, because they're not. And I mean, even if you put it on a mast, it says, oh yeah, mast mounted, and they give you 6 or 4 or 3 little things that are barely that long. Well, again, that's not a 20 lambda ground plane. Again, barely 1 lambda. It's probably more like half lambda, and it's all going to go like that. So your 6 dBs isn't going to go anywhere. So be very careful what you do. Now, this antenna, it's great. At least we've got it propagating. That's good. And what type of propagation do we get from it? Vertical propagation. Propagating in a vertical plane. Good. Now, here's our man in the car. I'm very good at driving cars without it. But I'm going to bend like that. What difference does that make? If I bend that antenna like that, what difference does it make? Answer, absolutely none. Absolutely none. It is still going to do exactly what that says on the tin like that.
That comes from the base rather than the tip.
Just gone up, and all I've done is bend it. I've just bent it. That's all I've done. Up there, bent it across there. And it is still...
It doesn't know what the shape of the actual thing in the top.
No, what it changes is the bandwidth. This antenna should give you a bandwidth of about 25% to the 2 to 1 points. Right? So if you go and measure it on your DNA, there it goes, 145, and then back out the other side, and the 2 to 1 points probably should go out 143 to about 148. Great. You bend it, and it all comes in. So it goes. Now, it comes in at 144, and 245, and out 146 to the 2 to 1 points. All of these things in design are very important. Right. Now I've bent it like that. Right. So we all understand that. We can actually bend that all the way down there, and it is still a vertical. I have made antennas, right, that are literally flat, square plates that go on top of motor vehicles. They are nothing more than that high. Their bandwidth is about 3%. Right? But they are still have monopole patterns. They are, just because they're flat plates like that, does not mean to say that they suddenly become horizontal antennas. They don't. And this is an interesting point, in fact. Right, here's a piece of magic. Here's our car. And here's our antenna. And I've bent it like that. And here's our 50-ohm point, if you like, coming off there like that. There's our 50-ohm. And I've told you that that's a vertical polarized antenna, because that's what it is. Now, here comes the magic. I'm going to change the ground plane to that long ground plane there. That's great, everybody, because it's all going to do what we want. Now I'm going to really do something. Scrub that. How many people in their home have got an inverted L? And how many people think that it's horizontally polarized? It's not. It's a vertically polarized antenna. I have done nothing than change the car into a piece of ground, or house, trees. This is now 80 meters or whatever it is you want it to be. But a number of people that think just because it goes up and then goes along here like this, think that it is a horizontal antenna. It's not. It is a vertical antenna, vertically radiated. You want a horizontal antenna, excuse me, 80 meters, then you need to go and put something up, you know, like that. So those are the sort of misconceptions that you get when you're doing
It's
this.
like got a bit of quarter wave on the ground.
That's called. It would be best if it's called. Or this.
That one, yeah.
That would be. Let's call that half wave or whatever you like to call it. That can be anything. We've already decided that can be anything. Go along there.
Well, she said you want an 80, you said you want an 80 metre horizontal.
Yeah.
So does that?
You've got to stick it up there and really get. And that's the other problem. That, for an 80 metre antenna, if you want this for 80 metres, you've got to remember that this thing here has got to be 20 metres above the ground for it to sort of work properly. But of course you've got houses in the way, you've got trees in the way. One of the things, by the way, that the Americans did a lot of research on during the Vietnam War was the use of tree radiators. They used to, if you like, you get a man sitting here with his transmitter unit, piece of wire, copper nail into the base of the tree and start transmitting. You laugh, that's exactly what they did. This is, I mean, specifically out in places like Vietnam where this is a very wet, sap-laden tree and therefore can conduct stuff up it. There's whole loads of learned papers in IEEE magazine. IEEE is the American equivalent of IEEE, all about the use of trees for radiating purposes on HF. This is not for radiating, 2,000 miles back to the USA. This is for radiating, if nothing else, 10 miles at best. But it's clandestine. You don't need to suddenly stick something up. All you need is a copper nail to stick in the tree. Right. Enough. Designing antennas. We're going to get away from... you want me to go now, do you? There's another 4.5 hours of this.
Right.
Right. Okay, enough. Some of the things I've sort of played about with so that it gives you some idea. What's the easiest way to make an antenna? The answer is a piece of wire. Right. Right, but you need to do other things with it. And what I'm going to sort of go through here, this little melange of stuff on the table, about 10 to 12 years ago, I wrote about 4 or 5 articles in Practical Wireless of making mobile antennas. I noticed that there was somebody asking questions in on the Facebook page, I think, or whatever it was, about what is the best mobile antenna to do and so on and so forth. And a lot of things are said about antennas, mobile antennas. They are incredibly inefficient. It doesn't mean to say that they're not resonant, because you can make it resonant, but they are still inefficient. That 300 ohms that I told you about suddenly diminishes down to 0.1 of an ohm. But you can improve things. Right, so this is one. I'll put it there. I can't stand it up. I think it'll probably topple over. So, right, before I do that, right, I'll just. This has been kicking around in my garage for ages. No, that's the wrong one, but it doesn't matter. Okay. Down here, we have the matching coil. This is where you find 50 ohms. So, this is fed from the base, and inside here, there's a tap point, probably somewhere up here, that makes it 50 ohms. This is a 40 metre antenna. So this has got to be quarter wavelength long. This has got to be 10 metres long. And at best it's going to be 2 metres. Now, we can either put loading coil all the way down here and then just have a width going up here, which is what a lot of the commercial ones do. They are incredibly inefficient because, basically speaking, what we call the radiation resistance, that is the resistance that makes the RF get into the big wide world, is low. It is about 0.1 to 0.5 of an ohm. We want it to be 300. Not ever going to get that. But if instead of putting the loading coil down the bottom, we put it halfway up, and then, if you like, put the rest of the antenna like that on top, till it becomes a truly resonant antenna. We've put most of the 10 metres goes in here. This now has a radiation resistance of about 4 ohms. Now that is an incredible difference. It makes a hell of a lot of difference. If this is 4 ohms as opposed to 0.1 of an ohm. What you're looking at is if you put a 100 watt transmitter in at the bottom, with a bottom loaded antenna, you're probably going to radiate at best 1 ohm. Sorry, 1 watt. 100 watts in, 1 watt out. In terms of efficiency. You now put this coil in the middle, and this is 4 ohms now. So put 100 ohms, 100 watts in the bottom, and now we're getting about 4 watts out. Now that's a lot of extra power we're getting out there. Now, if you've got some of you may have beams, and they're not halfway beams, they've got loading coils at the end. So if we now put a loading coil at the end, rather than where I had this one in the middle, so we've now got the loading coil at the end, this pulls up your resistance to something like about 10 ohms. And that makes a hell of a lot of difference. Mind you, that's if you are using something that's as short as this. Obviously, if you've got the more, obviously longer that you can make this dipole before you get to the coil, right, then the more you'll get towards your 300 ohms. So if you've got to keep the beam short and you've got to put a coil at the end, then the answer is that's where the place to put it, because that will keep your resistance higher and higher. So that's why you do that. Some of the things that I've used, by the way, as you can see, this is 4-inch diameter pipe used for, well, it's either waste pipe or it's used for tumble dryer things, etc., etc. So all of these things you can sort of buy at B&Q. So you can, most of the stuff that is here, you can buy easily and anywhere. It is no specialised stuff or anything. And these things cost literally a few pounds to make. Then there's nothing here that doesn't take a lot of expense to make, and I'll come on that later on. So that one replaces that, and I think that's an 80-metre one, but I have some for 40 and some for 20 and so on. Obviously, once you get above 20, you can do most of it just, yes, with a loading coil, because the antenna starts to become resonant in its own right. Again, I tend to use simple waste pipe, water pipe, plastic, white plastic. Do not use plastic that's this colour, because it is carbon loaded. And yes, it will work, and everything will look absolutely hunky-dory, but it would be like putting a whacking great big resistor into your system. But it'll have a lovely bandwidth. One of the other things that I have made, like this is a part of one, is making a coil like that and then putting a capacitor, connecting either end with a capacitor, and that makes the thing we call a trap. Basically speaking, a trap is a resonant length. So say for example that one, probably with 50 puff capacitor, probably would be a trap for 40 metre band. And I've got two on my antenna at home, just like that. If you're making an antenna like a trap dipole, they're very easy to make. So you know what the dipole lengths have to be, and you know where the traps have to be, because if you want a trap at 40 metres, then it's got to be at the 40 metre point along the line, or 20 metres, you put one in at 20 metres and so on. I have one at 20, I have one at 40. Just remember that you've got wire here that isn't part of the trap at one of the other frequencies. So you have to calculate how long that is and take that off of your dipole length and so on, plus a bit more. Now, one of the other things about designing antennas is the magic E number. Somebody mentioned at the beginning, when I asked the questions, what do you need? Somebody said, the speed of light. What is the speed of light? 300 Yes, fine. There you go. Except it's not. What the 300 da is the speed of light in what?
In a vacuum.
In a vacuum in space. Right. This is a coil that is sending an RF signal down it, and it is right. It is made of plastic and so on and so forth, and it's a coil and everything else, and the speed of light on this is not 300. It's roughly 0.75 of the speed of light. You've got to take that into account. Even when you make your dipole or your monopole, whatever it is, the RF travels down this, travels down there at the speed of light in whatever material that's made of, such as copper. Which means that if you make this exactly lambda by 2 for the speed of light, it will not work at the frequency you think it's going to work at, because this actually travels down here again at about 0.95 of the speed of light. So you shrink it a bit. This, you shrink it all a bit more, and so on and so forth. So all of those sort of things have to be taken into account when you're designing antennas. Right.
How do you measure the velocity factor of a strap?
The velocity factor is, how do you measure it? You look it up in the book. No, I tell you, the answer is, that's exactly what you do. You look it up in a book, because that's really, to actually calculate it, the equations are very difficult, right? So this simple thing to do is to look it up in a book. This is being, this is a coil, it's wound on PVC, so you look up the velocity factor of PVC.
I've tried looking at velocity factors before, different
Yeah.
materials, and can't find anything. Where's
If you go onto Google, you should be able to find velocity factors in materials. Yeah.
I found that, but so I wanted to find out what the velocity factor of a piece of aluminium was, for instance, for a given size.
Right. Most metals are in the region of 0.95 plus or minus 0.1.
Yeah.
So the answer is, don't worry about whether or not you're making it in copper, gold, or whatever.
Yeah.
Steel is the slowest, right? So it's more down to the 0.9 end. Copper and aluminium are up at 0.95. Gold is up at about 0.99, I think. But that's not the thing. That's less of the worry, is the fact that you're making it in copper or aluminium or steel. What is the big, as soon as you start getting into plastics, you really start slowing stuff down.
Yeah.
The best, or the least, let's say the best velocity factor will be something like PTFE. That would be about sort of, about 0.885. It's really quite good. Whereas you'll get other stuff that takes you all the way down to 0.5 and things like that. I mean, again, professionally, coax cable, we would use a thing called RG314, which is a PTFE based double screen coax with a solid centre. And the velocity factor down that is about 0.75 or something. Remember, so whereas if you go RG58, you're down at 0.66, 0.6 or something like that. So things to bear in mind. Right. Other useful things. I can't show you a whole one, but obviously a lot of these things need plugs and what's the names to go on the end. These plugs, it's a wonderful thing. Again, comes from Sainsbury's, Tesco's, Asda, and probably all the others. They do chopping boards, and the chopping boards are made out of polypropylene, and they make ever such useful things if you want to make antennas and plugs like this. I mean, that is sort of cut out with one of these. And you've got different sizes of those, and they sort of fit to different sizes of these. But this all comes from £2.50's worth of polypropylene board. So always things like that. I mean, I make literally everything out of the stuff you can get either from a supermarket, from B&Q, from Trago, whatever. Which brings me on to...
You use to hold it
yeah,
together.
sorry, go.
Sorry, does the glue that you use to hold it together, do you have to be careful of what glue you're using?
No, because I don't use glue.
Oh, fair enough. Have you held, are they just push fit?
No, they are held in, if you look, I've got holes around
right.
here, and I use very tiny little screws, and they're all held in with screws. No, I've never used glue. John?
What about random wire antennas that are not, percentage of, 80 metres?
Yep.
How efficient are they? So it's not multiple.
First of all, right, if it's lambda by 4 long, right, any antenna needs to be at least lambda by 4 long, and it will give you the full it'll give you the full radiation resistance. As you make the antenna longer, right, you'll get other factors coming into play, but it will still have the full radiation resistance. Okay? You only lose efficiency as you make the antenna smaller. And actually, you don't start losing out efficiency until it's below lambda by 10. So, here we are. Here's our antenna, lambda by 4. That's great. And it will produce its lovely pattern, and it's a full 300 ohm resonant antenna. Do that, and it's still a full, it's not resonant anymore because it's not the right length, but it is still fully efficient, 300 ohms. Now, if you like, we can get down here, and we'll now assume that that is lambda by 10, and we're still okay. What we've lost is bandwidth. Always remember that. This will give you 25% bandwidth on a decent, proper ground plane. 25% to the 2 to 1 point. That's how we normally measure this, to the 2 to 1 points, okay? The reason why we measure it to the 2 to 1 point, and if people are unaware of this, the actual loss due to the VSWR at 2 to 1 is 0.1 of a dB. Got that? That's all you've lost, 0.1 of a dB to the 2 to 1 point. Go to the 3 to 1 point and you lose half a dB. It's not until you get to the 6 to 1 that you start to lose 3 dBs. So anybody that says, oh, it's so much better, I've got the VSWR down from 1.5 down to 1.2 and it's going so much better, I'm getting more and more dBs out of it, is absolute rubbish. You're not. What you've done, usually, is to tune all the other rubbish out so that you're actually putting more power up into the actual antenna, but the antenna itself is still at the same level of efficiency as it originally was. That bit hasn't changed. It goes back to what I said on, the first thing about it being lambda by 2 or lambda by 4 if it's a monopole. etc., or just a dipole. So you're not losing anything. As soon as you get down to lambda by 10, you're still okay. But your bandwidth now, instead of being 25%, is probably only about 5%. As soon as we start going below lambda by 10, then our radiation efficiency starts to drop until we're down to very tiny amounts. And we're down to maybe 0.1 of an ohm, etc. And the bandwidth, of course, is barely 1% wide if you're lucky.
You will delirium.
Yeah. So remember that it's all of these things. It's back, and going back to what I said, you can't have out for out. Remember at our ball, right? It's all related that you.
So where does the transformer come into play then?
The transformer.
Yeah, so if you're using a random wire, say use a 90-watt transformer to bring down that voltage peak from can't quite remember what the voltage is, but it's certainly higher than 300 volts. And then warmer than that.
The impedance of a long wire can be like thousands of ohms, can't it?
Yeah,
That's why you use the transformer.
your transformer is. You're just using transformer into a long piece of wire. The answer is why? The only thing you're doing is the impedance matching your line, not the antenna. There's a difference. It's going back to what I said. The difference being is the antenna is producing what the antenna produces. You remember that there's a thing called the system, which is controls the antenna. Whatever it is, you've got it connected from the feed point of the antenna back down to your transmitter receiver point. And it's the system that you're looking at. And yeah, you add things like transformers and all manner of stuff. But generally speaking, you're not doing anything to the antenna. All you're doing is making sure that your transmitter receiver sees 50 ohms. And that is it. That's all you're doing. Making it's no other.
This is transformer, in layman's terms, putting it the same as having an ATU. So it's just making it so so your wire is transforming it so
I know,
okay in
right.
the radio.
When you've got one of these, and this is the difference. When you've got one of these, you probably pick up the scale that says VSWR. Yeah? That's the one you all look at, VSWR, because you think VSWR is magic. And it's the wrong scale to actually look at. What you really need to look at on this is that who knows what scale to look at on this?
Smith chart.
The,
Smith chart, isn't it?
yeah.
Impedance loss is all up.
You need to be looking at the Smith chart, because the Smith chart will show you exactly the level of impedance and capacitance that you need to get from your antenna back to a 50 ohm point, which, if you like, is exactly what an ATU does. It adds L and it adds C in either series, parallel, or whatever it is that your tuner unit does. And it's that Smith chart that basically you watch. If you set the Smith chart up and you can watch the dot, right, single frequency point, and you can watch that dot move all the way round, right, and then back again into the 50 ohm point, which is in the middle of the Smith chart.
Tell you what would be good then is if you did a presentation on using like a VNA.
Yeah.
Antenna,
The problem is,
antenna to
right,
explain to us.
yeah.
I can't understand it.
Unfortunately, I would do, but you really have to understand mathematics. And I mean really, because it contains real and imaginary numbers. Now, if you don't understand real and imaginary numbers, now, it will give you a point on there that says it is JE omega C. Oh, sorry, it'll be 1 over JE omega C. Or it'll say JE omega L. Now, how many people fully understand what JE and omega? No. So I would love to, but you really need to understand the mathematics of it. But a Smith chart is quite, it's a very useful thing to learn, but you really need to, if you like, go away and learn, or try and learn it, and when you've got a grasp of it, come back and ask me, and I'll try and help you. But to try and give a talk about Smith charts to everybody here,
Not necessarily
unfortunately,
about
would
but using an antenna analyzer to show you what.
yeah,
what
it's
some of the-
but it's trying to set everything up. That's, I don't know as whether or not I can. I'll have a look to see if I can do it.
You bring a non-resonant antenna in, plug it in.
You can't, because unfortunately a resonant antenna would automatically be compromised by this room.
Well, we could see
Yeah,
how efficient our antenna actually is.
Yeah, you,
We probably isn't very good.
but yeah. Am I doing all right?
You're
Right.
right, yeah.
All right, last by no means least, this is something that I cooked up. Literally, it took me about 5 or 6 hours. It's a 2-metre beam, which everybody thinks, oh yeah, that's a 2-metre beam. There's nothing special about that. No. How much would a 2-metre beam cost you? Lots.
Real terms,
Yeah, how much would a 2-metre beam cost?
probably about 60, 70 quid.
20 quid.
I paid 30 quid. Paid 6 quid.
Aluminium tubes. 4 feet long, £3.25, Trago Mills. 1, 2, 3, 4, 5, 6 of these. This is 6 element bit. Centre pipe, £2.50 from Trago Mills. It's used for shower curtains and things like that. And also, these are used for making lean-to stuff. And they also use the plasticky things like this, which helps you make one of those in the middle. That, the 2 of those cost 85p. You can copy this design from a book, that's fine, but you probably still need to tune it at the end of the day. This one, it's interesting because these, as you know, are called directors, and they're basically turning it into a beam. This one is not a director as such, although in lots of books it tells you that it's a director. It's not. In fact, it's a tuning unit. This is
why it's so close.
because this is in the near field of the actual radiating element. And so this is actually adding capacitance to this system here. I've added in here on my one, somebody was asking about that again, this thing called a palsy stub.
Yeah.
This is a length of coax, open at this end, and it's lambda by 4 long, though I think this one wants a bit of tweaking and tuning. But it's a lambda by 4 long, so that if you like, the coax cable comes in and the live side is connected there, but the earth side is connected to the live side of the coax cable, that then goes all the way down there and then all the way back and comes out and is attached to this side. So that is actually going lambda by 2. Now, and this is again where it's very useful to know about your Smith chart. A piece of coax cable is not just a transmission line that you think you can use willy-nilly. you have to be very, very careful with it, because this is a piece of coax cable, lambda by 4 long. What this means that if this was a short circuit here, you would see an open circuit at this point. And you think, okay, yes, it's an open circuit. But even if you actually shorted it, in RF terms, it would appear as an open circuit. Somebody else said something about the fact that one thing you must never do about antennas, and that is use a DC ohmmeter on your antenna, thinking, oh, like, you have to be very careful, because RF and DC are not the same thing. So when you've got pieces of cable, and this is something that you may have suddenly wondered about when you're connecting a coax cable into the back of your tuner unit, and it doesn't matter what you do, you can't get it to, even though you know your antenna is sort of okay and should be fine, you just can't get it to tune. And that's because your length of coax cable is probably resonant at the frequency that you're working at, and what you don't realise is that whatever is up the top there may be the inverse of what is at the bottom. So that may be reading absolute perfect, but because you've got a complete resonant length of coax cable in it, what's down there is totally different, and it just will not tune. You go and take off 2 meters, chop it off, put a new connector on, connect it up, works a treat. Yeah, and you just think, well, why is that? I took 2 meters off and it works. Or if you go and add an extender piece, 2 meters long, and suddenly it all works. And that's because you have to realise that the coax cable is not just a piece of DC connection between the top end and the bottom end. It's carrying RF, and the RF is playing in a completely different way to what you think the DC is doing. So all of that needs to take into account when you are designing and building your antennas, even if you are using commercially made stuff and you go out and add in your own bits of coax cable and such, that you could, something that seems to work perfectly well then suddenly doesn't. And you think, well, I don't understand, all the connectors are working and I've checked it and all the DC seems to be absolutely right. And all you may got to do to sort it all out is just either lock 2 meters off or put 2 meters on, and you get out of this part of the loop where it's just sort of going round and round the Smith dial. Instead of coming into the centre, which is what you wanted to do, it's just going round and round the outside. So there you go. So that's going back to this, the palsy stub, it's a lambda by 4 length. So it's seeing 50 ohms at this end. It's an open circuit at that end. And this open circuit is then reflected back down there, and it makes it appear to be a short circuit. So that's what
Do you
you get.
remember I brought in that radiating element of the
Yeah.
2 metre a couple of weeks back, didn't I? And that had a funny thing, it was like a loop. It wasn't an open-ended end, it was a loop, and it connected one side of the aerial to the other side of the aerial. It was a strange arrangement, and I couldn't understand it because, as you say, don't use DC. I used DC to try and it was all over the place.
The loop is probably adding phase. And you see, that's another
Yes.
thing that you're not.
I think you
Yes.
told me that at the
Yeah,
time. It's
that's
making that side 180 out of phase from that
it's
side.
adding phase to it. Yeah.
Crazy, crazy.
One,
Magic.
when I moved into my new house, I put a television area. I have to put it up in the loft because we're not allowed to put it on the outside. It has to go up in the loft. And so I went up, I put the antenna in the loft, connected it to the coax cables that were already up in the loft that the builders had put in. Went downstairs, plugged it in, absolutely nothing. Now this is quite bad because there's my wife saying, "Where's the television? You're the great antenna expert.
You didn't design
Where's my picture?" Right. Then, of course, as you would expect, the wife said, "Right, that's it, I'm going to get a professional in." I thought, okay, fine, that's what you want to do, get the professional in. So she got the professional in. He went up, he put the antenna in the loft, and he checked it, so came downstairs, plugged it in, plugged the television in, nothing. So he's scratching his head. And I said, yeah, that's exactly what I got. And then I had a brainwave. I thought, let's go and have a look at the coax socket in the wall that the builders have put in.
Oh, they haven't connected you.
Oh, it was connected.
I won't tell me.
Now, if you've ever taken or if you've ever installed a coax connector point socket on the wall, you know that you get the piece of coax, it comes out, you trim off about a centimetre at the most, pull back the braiding, and then you make a cut and you have the live side come out of the coax cable, and you just push that in, screw it all up, put it back on the wall. Oh no, this was installed by an electrician. So, what have you got to do? You've got to have lots of bits of wire. So, the coax cable comes in, and then he's got the earth going in where it's meant to go, and then the live side is stripped back, and it's about this long. And he's all the way round inside the box, and then connected it to the centre pin. And what this goes to show is that this length of wire is phased into the system, and basically it's wiping out the TV signal, the RF point. As far as he was concerned, DC meter worked perfectly, no problem at all, great. But he's not thinking RF, and that length is a phased length, and it just basically said, no, don't want to even know what is coming down this RF wise. So we just locked it off, connected it up properly, everything.
Perfect.
Happy wife.
What makes it annoying was, of course, my antenna that I put up, that my wife said I couldn't put up, would have worked perfectly as well. But there we go.
You paid the building price.
Yeah, actually, I did. I rang up the building people, and I said it's just cost me £170 to have an antenna installer come in and set this all up, etc. And it's your fault because your person that installed this has not installed it correctly. I took all the photographs, sent it all off, and a cheque for £170 came in the post about 2 weeks ago. Result. Anyway, time's moving on. Any questions that anybody wants to ask at all about what I've put forward?
In the early days.
I hope you've enjoyed the chat, and I hope you've enjoyed the. Try to make it as light-hearted as I can without trying to make it too technical.
Very, very informative.
Yes, sir.
Basically, you could probably tell from my accent, I come from London.
Yes.
And if anybody gets a chance to go into the Faraday Museum, I don't see anything round the wall that says Trago B&Q or anything. This bloke had to find the bits himself. So we need to thank Faraday for all the, you know, the work he did.
We made it. Polished wood.
There are some of us.
Yeah. Who remember Faraday? Oh, right.
No.
Speak for yourself.
This is very controversial.
Is it?
Yes, because Messrs. Faraday, Messrs. Hertz, and one or two others formulated a lot of theory about radio, all based upon radio waves.
Yeah.
And you go, yeah? What's wrong with that? The answer is a lot now. The reason why everything is based upon radio waves is because that's all they understood. They understood the idea of sound waves, and they've done loads of experiments on sound waves, and they could do waves in pools and ponds and all of that, and show all of the reflections, interferences and everything, and they understood everything in terms of waves. Nowadays, we have a thing called quantum physics. And if you like, some of all of this stuff about radio waves is being rewritten, because a lot of it is better explained by quantum physics than it ever is about radio waves. I have to put it this way. Do you understand the Heisenberg's uncertainty principle?
Of course we do.
Of course you do.
Well,
Yeah.
second nature to me.
That was on Star Trek.
Right. Heisenberg's uncertainty. Very quickly. Right. Heisenberg's uncertainty principle, basically, it's a bit like Schrodinger's cat. You all know about Schrodinger's cat. But Heisenberg's uncertainty principle says that if you have an electron, okay, it can be in two places at the same time, because you cannot measure actually where it is. So if you excite an electron here in this room with your transmitter, who is to say that it is also not excited in Australia in somebody's receiver at the same time? And that is down to Heisenberg's uncertainty principle. Right? There is a whole group of people who are looking at the whole business of the way in which, I'll still call them radio waves, work, but really it's not necessarily done by radio waves. For example, you go on about the reflections off the ionosphere. Radio waves reflect off the ionosphere. Why? Why should they? Why shouldn't they just go straight on through?
Frequency.
Yeah, no, you just said frequency. That don't mean anything. I'm sorry. I mean, if I put 2 meter signal up into space, it'll go straight through. It won't go back, come back again.
Ionisation of the atmosphere.
Right. If you look at it as a right, from your antenna, you release a particle. Right, from your antenna you release a particle, and it whizzes up to space, and it hits an ozone particle. And when that electron hits that ozone particle, it does a thing called, it promotes an electron in the ozone particle from one layer state into a higher state. That electron that's in the higher state then drops back into its lower state and emits an electron, which then goes down to the ground, and then you pick it up. That is far more sensible and has much more meaning to it, because that's exactly how the colour yellow works on that wall. A photon comes out of the light, hits that wall, it promotes an electron in the paint, right, that is pushed out, it then drops a mat back immediately and emits the colour yellow. And you see it as yellow. Great. Radio works in exactly the same way. You send out basically a charged particle, goes up to the sky, it gets promoted in the ozone and then drops back. And it's the dropping back emits more radiation that comes back down, and that's what you pick up on your bounce.
It's not reflected, it's just...
It's not reflected at all, it is, it's exactly the
it's
same as
remade.
why that wall is yellow.
Emitted.
It's a transference, isn't it?
And if you like, there's a whole load of science that goes,
Oh, yeah.
and it, no disrespect,
Some of the,
but it destroys a lot of what the early pioneers
We'll have a chat
felt
with
about
Brian
radio
Cox.
waves. Anyway,
Right.
it is very controversial, and I'm not going to go into it too much.
Thank you anyway.
Anyway, hope you've enjoyed that, and I hope you enjoyed it.
Well, what can I say? Has everybody learned something?
Yeah.
I know I have. There's a few things my mind has kind of gone. But no, seriously, that was a very, very interesting presentation, and many thanks, Chris, for coming along to do it for us.
Okay.
And I hope all our YouTube viewers, when you get to see this, will enjoy it as much as we've enjoyed it here in the club tonight. So thanks everybody for coming.
Thank you.